Hi everybody, my name is Jonathan and I am a data scientist and data engineer at a company called data.world, which is a data startup based in Austin, Texas. I think this is going to be really fun. I think that the three previous presentations were awesome. They described these derivative tools, brilliant derivative tools based on current census data and the way that the census disseminates that data. My presentation is going to be about a project that I did under NSF fellowship last summer in order to translate the fundamental data that's in the PUMS into a new format such that more derivative tools could be made using that new format. So without further ado, the first thing I want to do is talk a little bit about data.world, and this is my only slide about data.world. Like I said, this is where I work, and I guess I just want you all to know where I'm coming from. At data.world, we are on a mission to build the most meaningful, collaborative, and abundant data resource in the world. And we're doing this by dismantling the barriers between data and people with our platform that helps people work together to solve problems faster. So we're building a platform and a community. It's a social network for data people to find each other, to collaborate on data projects, and to work on data projects within the platform. A benefit of doing that is that other people might find your projects and join you, might improve your project, might use your project once you get it to a certain point, might use your project, expand on it, and send it back to you. Kind of the same way that GitHub really accelerated the realm of open source development. We're trying to do the same thing for data science. So enough about data.world. I'm going to get into this, by talking about my motivations, because I had this grant and I applied for it for very specific reasons. So I want to give you a little bit of my background of how I think and why I did what I did. So the first thing is there's a massive number of open data sets out there. Some estimates are that there are over 18 million open data sets currently available on the internet, which is more data sets than there were web pages available when Google was founded. I think that there's also news every single day about research and government accelerating that. The problem is, I think, that that this data is by and large growing in silos. And so individual efforts are stood up. They stand up their individual data portals to house their data with very little thought given to how their data is going to speak to other data that's out there. And then these silos really separate people, the data users, from the suppliers. So they put it into their silo, you bring up your truck, take out the data, and you process it offline. And then a lot of times that preparation work, the data wrangling that you do, it just sits on your hard drive, and nobody can use it. So this requires a lot of legwork on the part of the data user, and just to get that data to the point where you can do the real work, right? And I think data users spend a lot of time with specialized tools to massage this open data into a form where they can actually start the real work, where they can do exploratory analysis, and where they can build models on it. And this happens over and over and over again. If you have a question and I have the same question and we both go to the census to answer that question, and we both go into the source files, we're both destined to do the same prep work. And I think that this is just a massive waste of human effort, to be completely honest. It's kind of frustrating, the state of the world that we're in. So that, I think, pretty much sets up my motivation. This is a data crowd, so hopefully this rings true. So what if I told you that there's this technology that has been around for a long time, about a decade, and it's got well-hardened and well-standardized technology, and it's meant to address this exact question, this exact problem. Some people call it linked data, some people call it the Semantic Web, and some people call it RDF. It was invented by Tim Berners-Lee, who is the inventor of the World Wide Web, and that's essentially what it is. It's the World Wide Web architecture applied to data resources. So instead of linking documents together, you're linking actual data resources and concepts, the relationships that these concepts have with each other. So let's get into this. What does this exactly mean in practical steps? So the first thing is, as long as the data is in those individual documents, it's really boxed up, and the best thing that I can do is tell you where to find it and a little bit about what's in it. So we need a standard way of representing the individual bits that are inside those data sets. So first, you need to break your data into atomic facts. And these facts are often called triples, which comes from splitting them up into subject, predicate, and object. And here are a few examples. So first of all, Turkey is a country. Ankara is a city. Ankara is the capital of Turkey, right? So very easy. So this is a directed graph of two nodes with a predicate that links those two together. Semantic data is often represented as a graph when kind of going over its structure. There is also a way to represent this graph textually, which I'll get into. So you can see here how these triples hang together as a knowledge graph. So Ankara is a city, Ankara is the capital of Turkey, Turkey is a country. You can also notice here that Turkey is both the subject and the object of triples. So the next thing that you need to do in order to make your data linked is to use some sort of unique resource identifier so that I know what you're talking about and we both know what we're talking about and what we're not talking about. And the way that you do this is you just give it an address. So every single thing that goes into a graph database, a linked data graph database, has to have a unique address. And so that way, if I have a unique address that describes the state of Texas, which is where I'm from, and I point to it and you point to it, we're sharing knowledge. So here, like I said, there are a few different ways that you could represent this textually. This is about the rawest and dirtiest that it's ever going to look. This is just stating those addresses one after another in pieces of 3 with a period after it. This is called Ntriples. It's just the addresses stated like a sentence. So here you have Turkey. There's a data source out there called DBpedia, which is the graph database that has been pulled by, all of the information has been pulled by Wikipedia. So DBpedia resource Turkey has a W3 standard type of country. Ankara's type is city, Ankara's capital is Turkey. But this looks a little ugly, so you can actually clean it up a little bit by designating prefixes for those namespaces. I don't want to rewrite those namespaces every single time. So I'm going to designate RDF, DBpedia, and DBO as my prefixes, and then all you have to do is use those when defining what these triples are. So that's the code. That's about as deep into the weeds as I'm going to get. Here's putting it all together. The same structure of the graph looks the same. We're just getting a little bit more precise about how we're dealing with these concepts. And this brings up a question, right? Like, what's wrong with just calling Turkey Turkey as a string in a file? Well, there's Turkey the bird and there's Turkey the country. These are two distinct concepts, and they should be mapped as two distinct concepts out there. So there's a way that you can take care of this. So there are two resources. One is Turkey and one is Turkey bird. They both have the same name, Turkey, but they're different types. So, since format is very important, Tim Berners-Lee has posited this five-point scale, and up towards the top of the scale, he says that RDF, which is where you're using those unique resource identifiers to identify the concepts in your data, and then fully linking your open data to other sources so that we provide context to each other and linkages, is up there at the top of the scale. So why does this matter? When you model and distribute your data in a semantic web, you don't only make it available, but you also make it more usable. We're able to put the metadata with the PUMS. You have this data file, and then you have a separate data dictionary, right? With semantic technologies, we're actually able to combine those. So I'm not looking at coded values with opaque subject headers on a column header. I'm looking at agricultural sales, $2,500. I'm not looking at AGS 3, right? So we're able to mix that metadata into the data itself. And writing queries, you write queries like you would with kind of English terms. And it basically gives a better starting point for people who are uncovering your data for the first time and learning that schema because it's in that format. And it also helps machines learn faster because it's completely machine readable, which is why you see articles like this one, Why Semantics and Data Linking is Vital to Artificial Intelligence. This is something that I am profoundly interested in, and it's not something I'm going to really get into here, but spoiler alert, it it makes cognitive computing possible. So all this said, what did I do with the PUMS? I developed an RDF schema or taxonomy or an ontology. They're all basically forms of the same word to me for the ACS PUMS, and I hosted it on Amazon Web Service for everybody to use. So a little bit about what I did. These are the typical formats for the PUMS. You guys should be familiar with that. Getting started translating it from a tabular format into a graph is actually pretty easy, and there are automatic tools to do this. The first thing that you do is you treat every line item as a subject of a triple. Then the columns are the predicates of those triples, and then all the cell values are the objects of those triples. And then you just move on from there. You in a waterfall process, you just add more and more meaning into the data. And so here we have just a small section of what I'm talking about, where we have a fake housing unit that's given a prefix ACS. So housing 345 is of type ACS housing. It has an electricity cost, and that electricity cost is 123. So you can imagine more triples and more metadata added to this, right? So like, what exactly is 123? Is that, what units are those? Are those dollars? What's the time period of that? Is that monthly? Is that annually? What is that? And when is that a valid value? When was it valid a month ago? Was it a valid year ago? And so you can have these linkages and all this metadata connected to this idea of electricity cost. And then what else is connected to housing? Agricultural sales, gas usage, number of people in the house, et cetera, et cetera. And then what's connected to those? And so, aside from just making this really cool web of data, there are some actual benefits. And so you have, instead of flat tabular data, you've got these URIs that denote these linkable concepts, many of which exist in the real world. So this house might exist in Texas, it might exist in Virginia, and if I link those concepts of those states to other data sources, all of a sudden I have more information at my disposal because those linkages are explicit. And then the complex data dictionary, we no longer have that. The metadata is built into the data itself. And instead of these big unwieldy raw files, I've put the database in a secure. I put the data into a secure queryable database that's available in the cloud. So I do all this to make discovery of the data easier, to make it more interoperable, and to help machines learn faster. The machines learning faster bit is really where this becomes quite powerful because it's a completely machine-readable format, and those linkages are explicit. You are able to really enrich your data in profound ways. And so that ultimately comes to why I did this. I did this to provide the census in a new way as a center of gravity for other folks to link their data to the census. And I hope that people use this. It's available for free as an AWS public data set. You just go to aws.amazon.com/public datasets. You'll find it there. I've written all the documentation. It gives you a good entry point to get started with using it, and hopefully people will use it to develop derivative tools and apps to put this vital microdata information in the hands of users and in the hands of ordinary people to create a more informed public. So that's it. Thank you. That's my contact info.